Yes. Okay. I will talk today about the space radiation characterization because this is essentially make part of the research that I'm doing since 2017 inside a collaboration that is named AMS, that stands for Alpha Magnetic Spectrometer, that is a detector that is installed since 2011 on the International Space Station. And of course, it's a very big collaboration and no time to go in details, but I represent the group that is in the IMFN, the Italian Institute of Nuclear Physics, in the Sapienza division. Yes, this is something about myself. I'm in this kind of space activity since 2001 when I joined this collaboration. Before I have anyway the possibility to work in international collaboration in Roma, but also at CERN. I was taking part to the construction of one of the detectors. There was the one that discovered in 2012 a particle consistent with the boson. And okay, but right now the idea is to combine this expertise on measuring the cosmic rays, that is the same that are could have an impact for the health of the astronaut, with of course the fact that in the future it's clear from this first day, but also it's clear to anyone it will be it was planned by all the space agency before going to the moon and then going to Mars. So the space radiation, of course, space radiobiology is something that is a mixed up of three different disciplines, that astroparticle physics, because at the end the cosmic rays of the particles that are present in space are something that derive from astrophysical sources. There is the radiobiology, that is a discipline that address the effect of radiation, ionizing radiation on the human body or on the living things, and then the human space exploration, because if we plan to leave the LEO, the low Earth orbit, the particle that we encounter, the cosmic ray, will be completely different from the one that we receive on the Earth, but also on the International Space Station. This is why, because the Earth is a sort of cocoon, a place in which we can be very safe. Because we are very well protected by the geomagnetosphere that stop or deflect most of the charged particle, but also by the atmosphere, because when the cosmic ray, very energetic cosmic ray, will interact with the atmosphere, will create a so-called shower. That means that it will create a lot of different particles. And for our point of view, in doing that, we release most of their energy. So the particles that are created are different, but also less energetic. That means that are less harmful for the humans. So this is why the annual cosmic ray dose at the sea level, that is about 0.3 millisievert, is no real concern for us with respect to other sources of the background of radiation, the so-called background radiation. The cosmic ray in the heliosphere, the one that we encounter if we want to explore the space, are three different kinds of species. The one that originated outside the heliosphere, the so-called galactic cosmic ray. Then there are the ones that are generated by the solar activity that time to time create very energetic solar storm that could be very dangerous, and also the ones that are trapped in the particles that are trapped in the geomagnetosphere, the magnetic field that is around the Earth. Why this is a problem? Because if we can qualify in the radiation that is taken from the International Space Station with respect to the one that is taken on the Earth, the factor is roughly 10 times more. Completely different is the situation we want to live on the moon, stay on the Mars surface, or traveling the so-called deep space, or for example, in going to the moon or going to Mars. This is known from the very beginning of the space exploration era, I mean, so the Apollo mission, for example, is reported that the NASA engineer designed a trajectory to go through the Van Allen belt to reach the moon very carefully to avoid to the astronaut most of the possible radiation. And this is why, because as you can see on the right part of the slide, the radiation quality of the particle that can encounter in space could be very, very heavy. These black dots are correlated to the possible damage that are done by the radiation on the cells. From the left to the right, you see, for example, the possible damage created by a nitrogen or protons with respect to the iron particles, the heavier one. And also there is some, for example, a study that analyzed that the dose that the astronaut could have if they fly to the moon without any special, let me say, without taking carefully the design of the trajectory, could be heavier than the one that was measured during the Apollo mission, because of course during the Apollo mission the astronauts have some equipment named dosimeter that give the possibility to measure the dose of the quantity of radiation that was taken by the astronaut, and this was very low. But the possible danger is that the space radiation could represent for the astronaut is, for example, known from the very, very first time of the Apollo ages. But you can see here that in between the last two Apollo missions, the Apollo 16 and Apollo 17, there was a very, very impressive solar flare. That means solar storm, means particles that are produced by the sun, essentially protons, energetic protons, that are in a sense a storm because they last for a few days. They are not continuous. For example, you see here that these solar storms started the 1st of August 1972 and will end roughly 10 days after. So it's something that it could be very, very, let me say, short term, but there is no possible to forecast, or at least not on a long term, exactly as we are not able to make weather forecasts on the Earth to more than 5 to 6 days with accuracy. This solar storm had the ambition be taking place during August. Those inside the Apollo command module would have been shielded from 90% of the incoming radiation, because of course at the time the problem was clear for the NASA engineer. But however, even if the shielding being reduced, the dose, in case the module was in space during the solar storm, there could be some effect. And the effect of radiation could be of two different types. The acute radiation sickness, that means something that appears immediately after the exposition to radiation, or something that could appear later because there is a sort of interaction with the DNA that could create some problems, like, for example, the carcinogenics generation. Of course, this is the same if the astronaut in this kind of occasion could be in extravehicular activity, so without the protection heavy particular shielding. In case this kind of event should happen during the mission, of course, there was some plans to have some emergency procedure to abort the mission or to have an emergency return or landing, but of course this did not happen. So what about this kind of radiation? Of course, there are two different types of effects. The one that is created by this solar flare or solar storm, very, let me say, very short in time as duration. In this case, the radio protection criteria are the same that could be used on the Earth, that essentially consist in use of shielding. But for what regard instead the other components, the galactic components, that is less energetic, since this is in a sense continuous, the continuous exposure, there is no, this kind of protection could not be, the shielding protection could be not so effective. Then if we go deep on the problem of the moon, there is also another component that adds to the three components that I showed you before, that is the particles that are created by backscattering. What does it mean? That the particles incoming on the regoliths will generate by spallation, that means by sort of interaction with the regolith, some other particle, especially neutrons, that was measured. It could be, of course, again, could represent an alpha for the humans exposed to this kind of radiation. Of course, the idea is to try to identify the limit, because at the end, the astronauts are workers, like the workers on the Earth that are to be exposed to radiation, for example, in a nuclear plant or in some medical application, to, of course, identify the hazard and to, of course, identify some thresholds, some prevention, mitigation, countermeasure to allow safety space exploration. You see, the point is that up to now, we are not so much experienced. These represent the Earth, this graph here. The green ring is where this called LEO, low Earth orbit, where the International Space Station orbit. And you see that this ring is inside the Van Allen radiation band. That means that it's still protected from the Earth magnetic field. And instead, if we want to go, of course, to the moon, we have to leave this, or to Mars, we have to leave this kind of protection. Up to now, only 20 people, tens of people go there. So there is not many experience. What we did in the last 5 years is to use, of course, the scientific methods to try to work on the so-called dose-effect relations, but dose-effect relationship. But before to say something about that, I would like to say that we did it creating a collaboration with the people that in the hospital every day since the beginning of the last century use the radiation to diagnosis and treatment. And so they have a lot of experience about that. This is a sort of mandatory to investigate this kind of stuff. What does it mean, dose-effect relationship? We have, let's say, we have interested to understand how which is the behavior with the increase of the exposition to the radiation to the regard to the biological effect that could appear. And what we did, we of course start from creating a taxonomy. What is the state of the art of the knowledge? This is the first step of any investigation at the scientific level. Try to identify what is present in, of course, the literature, at the different type of experimental study, of course, also using data taking from the space mission, previous space missions. And of course, we published this kind of study. And just to go very quickly, the possible effect, of course, essentially from the so-called eye flashes that are some interaction with this particle, charged particle with the retina that creates some flashes in the eyes of the astronauts. This was reported from the first Apollo missions and many others, because essentially any health, any system of the body could be affected. Of course, generating carcinogenesis by interaction with the DNA, but also some less investigated system, like, for example, the cardiovascular system or the central nervous system could be affected. So for each one of these, we, of course, investigate the possible threshold. The threshold means how much is the radiation that could generate the possible effect. And we also make a sort of risk assessment to investigate, to try to assess which are what we think are the priority in investigation, taking in account that for the space mission in the future, in which the astronaut will be exposed for many days, not for, like, for example, in the Apollo mission, that the mission was very, very short in time. Not only the carcinogenesis could represent a problem, but also some effect that could be on the central nervous system, or some effect on the DNA could be really deep investigated. Of course, we also try to identify some possible interdisciplinary interaction that could be views in doing this kind of study and investigation. And we focus on of course, the synergy with the astroparticle experiments, because in the MS, of course, collaboration, we have a lot of experience in measuring the cosmic ray in details and with great accuracy. That means that we are able to measure all the possible charged particles, from the very light, like electrons or protons, to the very heavier, like the iron nuclei. And this is what, of course, we will try to investigate. So to increase our knowledge of to create especially some mathematical modeling that will allow us to, let me say, to predict with accuracy what will be expected for each particular space mission scenario, with respect to the possible damage that are expected for the human health. I think that I will leave the place with some questions, and thank you very much for your attention. And okay, and that's all. Thank you.